So, yes, that's about as good as it's going to get. Hi. Not yet. Yes? No? Yes? No? Wonderful. My name's Derek Kozel. I do software-defined radio for a living, a hobby, and sometimes as a way not to sleep. And, right, okay, so you can't see my slides. I see your problem. Well, I can kind of scoot over a bit more. It's fine. The rest of the content's all in the middle. Yes, and my talk is going to be bits to volts, programming the spectrum. I'm going to start with a brief introduction of what is radio, what is spectrum, and then what is software-defined radio, and then follow that into the actual programming bit. And I'll be advocating for at least 5 or 6 people in here minimum to go and buy one of these super cheap little software-defined radio receivers and get started with GNU Radio, which is a full and open source software-defined radio toolkit. Page down? Yeah, sure. Page down works. Yes. Introduction. Basics of radio theory. System architectures, not so much. But actually, here we go. You can actually see why I'm giving this talk. Because these notes are from the last Hardware Developers Didactic Galactic. And Chris saw me writing them and said, you should give a talk on that. And for some reason, I said yes. Oh, actually, that's going to block the other half of it, isn't it? Oh, there we go. That should be fine. Thanks. All right. Ready. No, that's not a page down button. Oh, what do you know? I'm just going to scroll. It's PDF. Scroll. Oh, God. Slide's long. All right, well, we're going to go straight to the demo part, apparently. Here's a software-defined radio system that's running. And so we're looking at broadcast FM right now. You can actually see this is one of the local radio stations around here. In the middle here, you can see the broadcast FM signal. So this is all analog modulation. You can actually see, when the station is quite silent, there's a very small amplitude on the signal, very small deviation, because it's frequency modulated. On the side here, you can see the digital audio sidebands. So if you have an HD receiver, you can actually tune in here and get some information. And it also carries RDS information. So this is the information that tells your radio receiver, you're tuned to this station, this track is playing. And so what we're looking at here is frequency, marked out by these small numbers here. So we're tuned to 98.9, 5, give or take, 98.0. Oh, I'm zoomed in, that's why the frequency is off. If I scroll. It's all a lot easier with a mouse. And hey, there we go. So the major sell here is that this is all being run off of a very small, tune that down, very small $20 receiver that you can get off of Amazon. The chips inside this were originally developed to be a digital TV tuner. So you're supposed to be able to plug this into your computer, hook it up to a little antenna, and watch TV. Somebody figured out that it was actually just spitting out raw samples of the radio receiver. And so you can write a little bit of extra software and demodulate FM. Or you can demodulate AM. Or you can demodulate a cellular base station, a satellite image. So if you were at Maker Faire and came by our booth, we actually had an antenna running, downloading satellite imagery using one of these. You can track planes, a whole bunch of different things. And so this particular receiver is called an RTL SDR receiver. And yeah, you've got sun in your eyes. Yeah, so they're $20 on Amazon. This software is called GQRX. It's fully open source. It's built upon the GNU Radio project. And in a few minutes, I'll go through what an actual flow graph looks like, where you can drag and drop components and start your own radio system using all pre-built blocks of software. When I was a kid, they had all those education programs where they're like, oh, you can drag and drop code. You're good to go. And it never was really very satisfying. The radio systems deliver a lot more. But for the moment, let's go up a bit higher. So if we go to about 150, if we're a little lucky, we'll actually see public safety FM. Oh, there we go. So that's a public safety radio right here. And so what this, so sorry, I skipped ahead a little. This is showing intensity at a certain frequency. So where this red spike was, you could see it there. Yeah, there we go again. So they're transmitting. And I can actually change this so that we're getting, let's go with upper sideband, just a much smaller receiver. And if they transmit again, we'd actually be able to hear it. But it's quite an intermittent signal. So you can see they have two different frequencies that they're kind of bouncing back and forth. So all we would actually hear is a bit of noise because this is a digital broadcast. But you can see how easy it is to start browsing through the spectrum there. And if we go up quite a bit higher, around 450, this is more public safety. This is actually narrowband FM. So what I'm doing over here is selecting the demodulation mode. And this is possible, again, because the hardware doesn't actually implement anything that's required to demodulate the signal. It doesn't know anything about what it's receiving, just that there's something. It's basically a high-speed oscilloscope with a little bit of radio front end so that you're able to tune to different frequencies. This one is a digital system. You can actually hear the baud rate there. If we look for one of these more intermittent ones, these have a better chance of being analog. But this actually looks like a trunked public safety system. If we keep going up a little bit more, so now we're going up to 700 megahertz. At 700 and, yeah, here we go. So this is a cellular band. So this is actually Verizon's uplink band for LTE. So one of the problems, though, is that this window is only looking at 2.5 megahertz worth of spectrum. This is great if you want to receive, the wideband FM that you've received in your car, or if you want to receive the narrowband FM that walkie-talkies and public safety tend to use. And there's software available that can demodulate those digital modes. But for a wideband signal like this, and if we go, actually, that's mirrored here, I should just be looking, it's just not wide enough to be able to see that. For that, we need a better radio. So I'm going to stop this one and switch over. And so this is GNU Radio. This is the same toolkit that was used to build the software that I was just running. And what we have here is a Usrp Source. So that's this radio that I have attached right here, just a small board, but it's able to receive much wider signals. Signals, in fact, that are 30 times wider. So up to 60 megahertz of simultaneous spectrum. And it can tune anywhere from 70 megahertz up to 6 gigahertz, which gives us quite the capability to, actually antenna RX2, quite the ability to look at different signals. And this is about as simple as a flow graph gets. We have one variable, which is our sample rate, which is going to be 50 megahertz, or 50 megasamples per second. That's fed into this block here. So if we pop this open, you can see all the different properties of it. Most of these are left at default right now. And then in RF options, we have another one, which is center frequency. And so this is going to be a slider, and that'll be all auto-generated for us, called center frequency in megahertz. So I'm taking that and multiplying it by 1 million. And then for RX gain, that's going to be our other slider. So that'll adjust how much gain we put onto our radio. And that'll determine basically how many signals we can bring in. And that's all advanced stuff, which you don't need. So this is sourcing the samples, sourcing the signal, and we're going to run that right into a sync. So this is going to be a display that we're running. And so if I hit this, who here knows how to program in Python? Oh yeah, all of this front end is written in Python. Who here knows C++? Most of the lower level code is written in C++ for the performance. So by clicking this button, I've just generated the flow graph, and actually says generating topblock.py. And so if I pull up my editor, yes, I realize it's been changed on disk. This is the Python code that it's just generated, and I'll snap that over to the side for you. There we go. So a whole bunch of imports. GNU Radio is the library that it's using. If we scroll down, you can see a whole bunch of just the setup. The variables, we've got our sample rate, we have our RX gain, we have our center frequency with all their default values. And then there's the blocks. So these are the blocks that we're looking at here, and they all get wired up and instantiated with their default values and the values that you've selected here. And a bunch of these get wired together. And then down here are a bunch of so here they're getting wired together. So we're connecting the Usrp source to this phosphor sink. And you'll see what phosphor is in just a minute. A bunch of the closing events, setting the sample rate, and because this is all going to be interactive, these things get called by the different graphical sliders. Wonderful, but what does it look like? Firing up. And there's a phosphor sink. So right now, what was my default frequency? I think 1 gigahertz. Yes, I'll put that over there so you can see it. So we're at a gain of 30, and we're at 1,000 megahertz. It's not very much here, though. So let's say, what was it? I just slide along here. We should find the Wi-Fi band. Ah, we just passed it. Come on. There we go. Wi-Fi. Let's get a bit more gain. So what this display allows us to do is see very, very intermittent signals. Oh, come on. And unfortunately, the lights are glaring it out a bit, but you can actually see the packets flying by in the display here. So this is a much wider signal. Right now, we're looking at 50 megahertz worth of spectrum from minus 25 to plus 25 off of the center frequency here. And it's a bit hard to see, but you can actually see that most of the time, it's not transmitting. So this is a histogram of the power. So we're seeing small spikes here that are showing when the Wi-Fi is actually transmitting. If one of us pulled out a phone or something and started firing up YouTube on the Wi-Fi, this would basically just max out. Well, depending on your connection. So at 782, this is the LTE band again. Not many Verizon folks around, and this is overpowering a little. There we go. There we go. So actually, that leads into one of the things I had in my presentation that I'm sorry that I messed up my slides. If you don't have a filter in front, which I don't right now I just have USB in one end, an antenna in the other, and that's it. If you have a strong signal nearby, which we do have some, it'll overload your front end, and as you can see, we weren't actually receiving anything until I lowered the amplification. So let's tune this over. So here we can see a much better picture of the LTE uplink bands. Nice, wonderful, pretty pictures, love them. But you don't actually, there's no understanding of what the information is that's flowing by here. So this is a great display, but it's not actually decoding anything. We basically have a glorified spectrum analyzer. So then you get to this sort of a mess. So remember how I said that there were those digital sidebands on the FM receiver? So this flow graph actually goes through and demodulates all of that. So I'll switch my antenna over to the other radio. Hit play. And 98.9 was the station that I was getting. Failed to open RT. Oh, because I still have the other one running. Somewhere. Everybody likes permissions problems, right? There we go. Much more reasonable. So here we have our same Mexican radio station that we're receiving. We can see there's a very strong signal right in here. And so we're tuned to 98.9 megahertz. Got your strong signal here, but then there's also some information out on the side there. So if we start working through the tabs, this is called the baseband. This is your basic signal And right now we're looking at a width of 2.4 megahertz, which is much wider than your actual broadcast FM signal. You can demodulate it, and this is, maybe you've seen one of those visualizations on an audio player when you're listening to music, and you can see, here's the low frequency sound, and then right up, so in kilohertz, 20 kilohertz, right about here is as high as the human ear can listen to. So everything above this is stuff that you wouldn't be able to hear out of your radio. It's not music. And so that's where they actually store all this digital information, is in the frequencies that the human ear can't hear. So this is the left plus right, the pilot. So this is the actual main carrier frequency. Not very interesting. But here's our digital sideband suppressed carrier subcarrier. So this is the digital information being stored right here. And the RDS looking a bit on a wider spectrum. Left minus right. RDS constellation. It's not actually. Sorry? RDS is the digital information that's being transmitted. It's the system of transmitting the digital information that decodes into the station information. So you can see that this is actually the decoded output here. So sombrero, it's a children's program. If I pull the screen wider, yeah, there we go. Debajo del sombrero. Don't judge me on my Spanish. Much better. Yeah, and so if I increase the gain a little bit, we should get this resolving a bit better. There we go. So this is the digital information. Digital ones and zeros. This is not a very complicated signal at all, and so it's transmitting ones or zeros. And there's a bit of encoding on top of that, so if you start diving into communications theory, you realize there's a lot of benefit to putting in some redundancy and putting in some channel coding so that if you get some noise, you don't get garbage out here. But fundamentally, you can take this, and this is called a constellation. And this is taking the demodulated output and saying, okay, it'll group these and say, well, that's one type of signal, and that's another type of signal. So these are your symbols. And we're seeing lots and lots of symbols overlaid because this is transmitting fairly quickly, and it's sampling extremely quickly. But yeah, so it decodes it. And down at the bottom of the screen here, you can actually see the full output. I'll pull up another view on that. There we go. And if I scroll up a little, I find it pauses it. So we can see, here's one whole message here. The radio text, so this is what we'd be displaying. The program type is children's programs, some information about regions, language, yeah, and then the type of message that's being sent. And again, all of this is free and open source software, so you could go home, you could download this and try it out at home. And all you need is one of these little $20 receivers. I'm not using the more powerful one right now. And so if I drag this over a bit, you'll be able to see a bit better. So again, we have a radio source. We have a filter in the digital side. So again, if there's a powerful signal, this won't help me at all. But it's a signal. And then it's going into a wideband FM receiver. And it's demodulating the entire signal there. And then it breaks out into the different tabs that we saw there. So that path goes to RDS. The first screen that we were looking at here, title is Baseband. This is a GUI, fast Fourier transform sync. So the fast Fourier transform is a mathematical operation that takes this oscilloscope data that we're essentially getting, the time data, and it translates it into the frequency domain so that we get a plot that looks like this. So we can see the energy at different frequencies, and then it's changing over time. And it's as simple as just dragging down these three blocks, and you would be seeing that same frequency data. Then it gets demodulated. This, I believe, oh no. And so it gets demodulated, and you get another waterfall sync that says waterfall plot. And so that was the final tab on that previous one. We have 3 sliders again, one for gain, one for frequency, one for volume. I can drag this in. There's another frequency sync fast Fourier transform sync. So we're seeing the spectrum, and this is of the FM demod. So that's the actual audio spectrum that you see. And these blocks are all included in the default distribution of GNU Radio, which you can download. It works on Windows, it works on Linux, it works on Mac, and there's tons of examples that cover all of this. And I won't go into all the detail of this, but down here is actually the magic block that's doing the digital decoding. So the modulation type of the RDS is basically phase shift keying. And I had some very pretty slides talking about this, so instead I'll draw it. Sorry, I'm not tipping anything, I hope. No, oh, that's not going to help. There we go. Not going on myself. So if you take a basic sine wave, looks like that. And it's not, so we're going over time. Sorry? Yeah, sure. If you have a sine wave over time and say this is, voltage. So this is what you would actually be seeing on an antenna if you just had one sine wave coming in. But this isn't carrying any information. So what you can do is various different types, such as frequency modulation, or amplitude modulation, or phase modulation. So we had another one of these plots, and you wanted to transmit like a digital FM signal. So we're going to go, we're going to transmit a 1, 0, 1, 0. You might see something like, well, actually that'd be phase, sorry, but ignore that a little bit. And that should all be the same height, because we would call that a constant amplitude signal. We'd only changing the frequency of the sine wave. So that's that's the basic FM. Then if you had an amplitude one, you would go, maybe 1 is the really tall signal, then you have a much smaller one, and a tall one again, and a small. Phase shift keying is what I accidentally drew here. So you have a sine wave that's going along, and then when it hits this transition point, and of course this depends on your encoding, but the most basic way of thinking about it is it changes phase in some way. So this would be a 180-degree phase shift, but there's a whole bunch of different versions. And it would do it again here, and again there. And there's different ways of doing these phase shifts. You can have a 90-degree phase shift, 180, and it starts getting complicated. But what that allows you to do is pack in more data if you start adding that complexity. Because here we're just sending either a 1 or a 0 for each one of these sample periods. So we're not sending very much data here. Another way of looking at that is if you had, a plot, you could say, if this was amplitude and this was frequency, though this isn't what it ends up being. So if this is frequency and this is amplitude, we could say, well, we're going to transmit really high frequency or really low frequency, 1 or 0, bouncing back and forth. Well, what if we also said, okay, you can transmit the really low frequency, but you could also have it low amplitude or high amplitude. You'd have another data point up here, and there, and there, and there. I'll go with X's for these ones. So now we're able to send 2 bits of data for each sample period, because you can be at each one of these constellation points. And you could add another axis, which is the phase shift, and you could get into a really complicated setup. And that's how they pack in more and more data. So if you remember the old phone dial-up modems, the way that they ended up getting to higher and higher and higher data rates was they packed in more and more and more data points in here. But can anyone guess what the problem is when you start packing in lots of these points? Yeah. So if you get a little bit of noise, say somebody else comes along, transmit on your same frequency or very close to it, and all of a sudden, this point jumps up a bit. Now it's kind of there. Well, is that this point here? Is that point there? You don't really know. So you end up with these growing out, and all of a sudden they start running into each other, and it gets harder and harder to tell which one of these symbols is the correct one. And so they do lots and lots of fancy tricks to make sure that this doesn't happen. But it's reality. So it does. You make mistakes, and you guess the wrong one. And all of a sudden now, when you have a lot of information packed into a single symbol, you're not just getting 1 bit wrong. You're getting 5 bits wrong, 10 bits wrong. You know. And so they do a lot of smart things to try and minimize that and transmit redundancy and all that. But they've gotten up to constellations where you have 1,024 different points or more. And that starts getting very, very dense. But it gets you your YouTube video really, really fast. Does anyone have any questions, by the way? I've just been going on. I apologize again for my slides. I'll try and fix those in a moment. But yes?
Constellation scope on software, there was probably 0 and 1, and sometimes it was making a circle, some kind of noise, I guess. Could you
Yes.
have an explanation for that?
Yes, absolutely. So if we go back to this constellation map,
Just now.
you can see here it's both losing synchronization and it's not getting enough noise, and so it can tell. It can tell that there's a signal there because we're not sitting at just 0. So there's stuff there, but this isn't a very good receiver, and so it partially ends up losing track. So the phase information and the amplitude information gets a bit messed up. The frequency's a little offset. This thing is actually getting piping hot at the moment, and with temperature it'll change what frequency it's tuned to, and so. Yeah, when we're seeing it clustered, we're seeing the noise, and when we're seeing that, it's losing its synchronization. One thing that we're not seeing here that's a really cool plot that I wish I had at hand is we have, sorry, I'll pull this over again. We have this plot here, and we have a cluster of symbols here and a cluster of symbols here. But, of course, we're not, sorry, I'll switch back over to Editor tab. It's not instantaneously able to jump from one to the other. It's an analog world, it's an imperfect world. So there's a whole bunch of samples in the middle, which are along this line, because it's transitioning back and forth. And of course, we're seeing data points out here, so you end up with all these lines going like that. It gets really fuzzy. So if you accidentally sample somewhere in the middle, because you're sampling really, really fast, and you think that that's a symbol, that's called inter-symbol interference, because you're seeing something that's not actually meant to be decoded. So you need to be sampling at exactly the right time. And so GNU Radio has time synchronization blocks that help you figure out when the transmitter sent a symbol and how frequently you should be sampling, and aligns you with that. And of course, if you have samples up here, you end up with this really pretty diagram where it forms a box and then it crosses over. And so you end up with this really pretty plot that I wish I had a picture of. The presentation will have a picture of it by the time you see it. So sorry, yes?
What kind of antenna are you using?
So right now, I am using a super cheap little dipole antenna that I can untangle. Looks a lot like this. Well, actually, it looks exactly like this because it is this. It's got a little magnetic mount on the bottom. This actually ends up only being half of an antenna. So if I were to just stick this on here, we'd get really terrible reception. So instead, I have it stuck to the bottom of this stand, which is metal. And the metal plane there is actually forming the other half of the antenna. And there's a whole variety of different antennas that you can get with that. It helps if it's electrically connected. That's a different type of antenna as well.
Is the antenna supposed to be proportional to the wavelength?
Yes. It's a very bad antenna. So, give me 30 seconds here with my LaTeX, and we'll see if I can delete out what I was trying to do. Got a beginning of a frame, an end of a frame. Can you itemize?
It's that.
Who I admit it. I didn't commit all that recently. Hey. Oh, it's still 2 slides. Tech. Frame, make table. I'm very confused about why this was rendering up until about 5 minutes before the talk. But I suppose control, what is it?
We can read the slide on the back.
Yeah! We like text, right?
That's a new way to look at a slideshow. For real text.
This is when you know you're in San Francisco. I'm sorry, my presentation didn't work, so you're gonna have to look at it. What is it? Just Control minus. Anyways, this isn't very helpful, but one of the things that I wanted to talk about was filters, because if you put a filter out in front of these, you get much better reception. One of the limitations that you end up with a software-defined radio is that because you have, for reception, if you're looking at reception, you have an analog to digital converter that's sampling the waveform of your radio signal very, very quickly. But it only has so much resolution. So I guess I'll just keep using this as my presentation. I'm glad you guys don't use the paper for anything else, Chris, given that this is still here from last time. Pull this all the way across. There we go. So again, if you have a waveform that's like that, but say we had a really, really cheap analog to digital converter that only had 4 different levels, and you managed to center it around the center, what you would end up with is, it's 0, and somewhere around here it jumps up, and it's gone to another level, drops down. You would end up with something that's still I'm drawing this rather badly, but you get the idea. It's a quantized sine wave. And so there's an error here. You end up with, and that ends up contributing to the system noise, because these transitions are very, very high frequency, and you start doing the math, and you end up with a bunch more system noise in there. And so that degrades the quality of the signal that you're receiving. So you want to have as many bits as possible. This little cheap receiver has 8 bits. So you only get 256 levels of signal there. The slightly larger brother has a 12-bit ADC, and it's sampling much more quickly, and it's actually doing decimation, so you get 13 bits or so of information. So you
lost a microphone.
Ah. 5 minutes ago. All right. So this is quantization noise, and the other thing that the resolution of the ADC limits you at is if you have a signal, so this is over frequency now, and you have a very, very strong signal here, and then you have a tiny little signal right next to it, or somewhere within the range that you're looking at. So we're looking at this range here. If your ADC isn't high enough resolution, you don't have dynamic range, the ability to both resolve a little signal here and a strong signal. And so that dynamic range can be helped out. If you want to see this signal and you have a filter that will only pass frequencies in this range, you can basically attenuate out. You can reduce the power of this signal, reduce the amount of energy at that frequency that actually reaches your receiver. And so then you can tune over and see it just fine, because you can increase your gain and make this into a big signal that even with your quantization noise and everything else, you can still resolve. Filters, amplifiers, especially this is a really terrible receiver. It has a lot of its own noise. And so if you put an amplifier out in front of it, a lot of the folks who use these to receive airplane data will put an amplifier and a filter out in front. So they're only looking at the frequencies of interest. And because these are fairly weak signals from airplanes flying around, they'll put in an amplifier that'll increase the level of the signal before it even hits this. And you can get a much better signal reception. at Maker Faire, we were still getting 30, 40 miles of reception with one of these without an amplifier, but with a filter. And then with an amplifier at home, I get about 150 miles of range.
What frequency is
The
the airplane data?
airplane data, ADS-B, is at 1.09 megahertz, 1090 megahertz, which these will easily cover. So this one works from 24 megahertz to 1.7 gigahertz. This one here is 70 megahertz to 6 gigahertz. Power amplifiers. Yeah, so some example systems, which I'll wrap up with, because again, my selling point here is that you should go and you should get the $20 one and have fun with it. And then when you finish having fun with this, which won't be anytime soon, you can get one of the other receivers. And so this is an RTL. It goes from 24 megahertz to 1.7 gigahertz. It has a sample rate of, give or take, 2.8 to 3.2 megasamples per second, and that defines on how big of a window of spectrum you can view. It has an 8-bit ADC, it works over USB 2, and it's $10 to $20. Kind of the next level up at the moment is the Hack RF. It was designed by Mike Osmond and Jared Boone. The driver for this is open source, but pretty much all the hardware is closed, even though it's very well understood, and you can find the data sheets for the chips. And there are some open hardware versions of this. It's a half duplex transceiver, though, so you can actually transmit with it. Transmit or receive one at a time from 1 megahertz to 6 gigahertz up to 20 megasamples per second, so you can view 20 megahertz with the spectrum, which is just barely enough to see a full Wi-Fi signal. And GNU Radio actually has blocks for demodulating the Wi-Fi, so you can actually see some of the channel information in the data. Still over USB 2, still with 8-bit ADCs, and that's $300 right now. There's the Lime SDR, which is coming out sometime quite soon, which is about $250, and has 2 channels, but we don't know a lot about its software support in practice yet. The Blade RF has been out for a few years. It's a full open hardware design, so you can download the full schematics, and I think even the Gerbers for it. 300 megahertz to 3.8 gigahertz, 40 megasamples per second, so we've doubled our bandwidth again. 12-bit ADCs and DACs, fantastic, but the price has gone up again to $420. These all have GNU Radio support, which was one of my criteria for having it on the list. And then finally, not entirely just as a shim for the company I work for, the B200 and B200 Mini, which I'll pass around in just a second, go from 70 megahertz to 6 gigahertz. You can sample up to 61.44 megasamples. That weird number is actually because it's very convenient for telecommunications. Some of the protocols that they use work at divisors of that. 12-bit ADCs and DACs, USB 3, and it's $680. Schematics for that are online as well, and the drivers on GitHub, as it is for the Blade RF and Hack RF. Yeah, GNU Radio, GNURadio.org is the website. Free to download. It's all open source. There's some tutorials and other things like that. So I'm going to pass these around, and if you have any questions, I think I still have maybe a minute or two, and I'd be happy to answer them. So pass that there, and one to you, and you. Yes?
Are there any general rules of thumb for data rates compared to frequency and encoding versus really complicated constellations?
Sure. So one of the things I didn't get to was if you have one of these ones that will transmit, be careful where you transmit, because a lot of the spectrum is licensed. And that's the Federal Communication Commission considers the wireless spectrum to be a shared public resource. And so the limitations on what you can transmit come both from physics, but also the FCC will say you can only use this type of modulation in this frequency range. As a matter of practice, a lot of the long-range communications happen at low frequencies because they'll actually bounce off of the atmosphere, so you can reach from here to the UK quite easily. If you want to do high data rate, though, there's a fundamental limit called, based on Shannon's theorem, was a professor who defined this, on how much information you can pack into 1 hertz of spectrum. And so If you want to send more data, and fairly easily, then you need a wider and wider signal. If you have a 20 megahertz wide Wi-Fi signal, you're taking up, and you put it down at 10 megahertz, you take up everything from DC to 20 megahertz, which is a huge amount of communications at the moment. So they shoved that up at 2.4 gigahertz, where there's just free room for days. Well, not anymore at 2.4 or 5.8, but amateur radio is kind of the easiest way in the United States of getting access to frequencies and the ability to transmit on them. You can transmit up to 1,500 watts. The question set for the exam is actually published online, so I really push it as a great way of getting access to spectrum. And at 10 gigahertz, we have 500 megahertz worth of spectrum from 10.0 to 10.5. So you can transmit almost anything you want on those bands. The FCC adds the requirement that you can't have it be encrypted, and they have some restrictions on like ultra wideband signals and spread spectrum on the lower bands. Yes?
What do you use it for?
What do I use software-defined radio for?
No, but I mean,
All
what do
right.
you use that spectrum for?
Oh, the 10 to 10.5. So I'm doing two things with it at the moment. There's a society or club just down in San Jose, where there's about 30 of us who have radios capable of transmitting there, and we hike up mountaintops and talk to each other, generally over basic FM, narrowband FM signals. But what I'm trying to encourage is more and more use of software-defined radios of whatever type, and generate more and more digital signals and wideband signals. And so my current project is to bounce essentially Wi-Fi off of the moon. And so I have a 12-foot wide satellite dish and a 200-watt amplifier. And you have to make some changes to it, so you can't quite use Wi-Fi because it takes too long. Your connections time out. Who knew? But you can absolutely get a signal to and from the moon, even at 10 watts, with digital encoding. And then amateur radio as a hobby has lots of uses for various things. Yes?
Are you allowed to transmit at 200 watts?
Yes, you are. At 10 gigahertz, at the low end of 10 gigahertz, you have to be careful in the US because the government runs radar at that same frequency, and there's a lot of stuff that's coming like on road radar and stuff like that. But if you have a satellite dish pointed at the moon, one of the choices that you get with antennas is how much gain you get, and that basically always comes at the cost of directionality. And so a dipole radiates in basically a donut shape around it. If you have a satellite dish, you have this kind of pear shape looking up straight along the axis of the satellite dish. And so for a 12-foot dish at 10 gigahertz, that's less than a degree wide. It's about 0.4 degrees, which almost perfectly matches the moon. So you have to steer it very carefully. Any other questions?
Can you receive iridium signals on cheap helmets?
Yes. I forget what frequency Iridium is at, but I think so. And there was a talk at the Chaos Communications Congress a year ago where they actually figured out how to demodulate the Iridium signals, and it turns out they're not encrypted. Oops. And there's now support for that in GNU Radio. So you can drag and drop the GR Iridium sync, and it will demodulate it and drop out audio files for you. Yes?
Do you have any suggestion of either Usrp or other SDR from Wi-Fi and analysis for the power on the really cheap side?
Well, the EDIS research one, of course. The EDIS research one is not actually a bad choice. I do. So I'll explain both why I like it and why I think the other ones will work for you, absolutely, but do have caveats. That one we specifically designed to be as low cost as we could go without sacrificing performance. So that gets used right now in towns in the United States, Canada, Mexico, and Africa as the only source of cell service. So it is that kind of grade of radio. You can put in good references, it's stable, it has good software support. It'll go across your bands, and it's wide enough. The Blade RF is also not a bad choice at all. They have pretty good software support. It's a little flaky in spots, but it is quite good, and it actually beats ours in one or two spots. that hopefully will be fixed by the end of the week because I found the problem. But like until very recently, they could only accept a rather odd reference frequency. So they can finally take in a 10 megahertz reference, which is kind of the industry standard. So if you're just playing around, or if you just want something casual, you can save $200 and go with the Blade RF. The Hack RF it just wouldn't work for you. It's not fast enough, and it doesn't have the type of stability and performance you need.
So there's no Chinese clone or whatever trick like the one you just...
I really haven't looked, but I have not heard of any. The Lime SDR at $250 is really, really scratching the bottom of the barrel. Yeah, definitely. Yes?
When you were talking through the spectrogram, you mentioned that these signals weren't demodulated yet at that point. But I'm confused because you've only got 50 megasamples of bandwidth in the radio. So is there a stage of demodulation that's happening before that? Or?
So what's happening is there's down mixing happening. So you have, last sheet of paper, I promise, and then last question if you want. Okay. So make it this nice and long. So if we have our FM radio signal, our broadcast FM at 98.9 megahertz, and we're only able to see, 50. Well, okay, so let's say we're using the cheap one, so we can only see, 2.5 megahertz there. Obviously, we can't receive this directly. So what you have on board is you have a local oscillator, something that's generating a sine wave, and you have a mixer. And because math and physics are wonderful, hey, I've got a minute here. If you tune that oscillator to be 98.0, it'll take this signal and it'll produce a copy of it at half the amplitude and some loss and other things right down at your frequency, right down in your baseband. So that's again your baseband here. And so that's what we were seeing happening. And then entertainingly, you would end up with another copy of it up at almost 200 megahertz, 199 and change.
So part of your software defining is that down mixing?
So the radio, that is basically the only responsibility of the radio, is to do that down mixing. Maybe a little bit of filtering depending on which one you get. And then the B200 has an FPGA, and the Blade RF have an FPGA on it, and possibly the Lime SDR, I forget, have FPGAs on them, and they have a small amount of digital signal processing built in. There's an opportunity there for you to implement custom code onto any one of those and do some signal processing there. But fundamentally, what you end up doing is just getting, an analog to digital conversion at your sample rate of this baseband signal. And that could contain the actual information carried there, could be anything. And then you implement all of the logic for demodulating the AM, the FM, the iridium in software. Okay, that's me. Thank you very much. And
What's your GitHub?
my slide deck really wasn't that bad, I swear. So my GitHub is just my name, D Kozel, Derek Kozel, D Kozel. But I will make sure that it goes up on the Meetup website and that it's posted out there. Thank you.